So, we now are at the last part of this course, which is on trying to look into fluid flows that we have studied in the course. We have studied various kinds of fluid flows in the course. We have done flow through a channel, we have done flow between two concentric cylinders, we have then done extensively worked on boundary layers over flat plates, etc. But a question that always remains is that whatever we have been deriving in the class, all the flows that we have been looking into in the class, do these flows continue to remain so when you are observing them in reality? So, say for instance, if you are trying to push fluid between two flat plates, which is what we did in the channel flow problem, there is a pressure driven flow through a rectangular geometry. Would you observe the same parabolic velocity profile irrespective of the pressure drop? So, this is basically a first question to ask. Yes, we got the parabolic velocity profile, but would that be something that you would observe forever? And in the same light, for the flat plate problem, we discussed about a uniform flow over a flat plate, and we saw that the boundary layer basically continues to keep growing as you move down the plate. The ideas of separation that we learned, where we said that the velocity field effectively was, if it was a decelerating velocity field, at some point when the shear stress goes to 0, the flow separates. In flat plate, that doesn't work, because in flat plate, if you remember, the imposed flow is uniform, which means the pressure gradient in the flow direction is 0. It's a 0 pressure gradient flat plate boundary layer. So, if the pressure gradient is 0, that means the curvature dou square u dou y square is 0 at the plate for all locations. So, the criteria that we learned for separation becomes a little fuzzy when you are thinking of a flat plate. So, then you are bound to ask the question that would a flat plate boundary layer where you have a uniform stream incident on the plate, the Blasius problem, we learned that there is a Navier-Stokes close to the leading edge. There is Prandtl's equation to be used in its full entirety after that particular distance. And then you have the loss of memory of your initial condition and you have a Blasius solution. But we never said anything what happens further beyond. Can the Reynolds number, if you define Rex, the Reynolds number based on the distance travelled along the plate, if it becomes arbitrarily large, how large can it be? Can it continue to be as large as possible? And we saw some hint of this when we looked into those early experiments of skin friction measurement done by Dhawan. So, in those experiments you saw that the skin friction as a function of Rex, it followed the Blasius theory prediction, which is basically going as 1 by square root Rel or Rex actually for the skin friction. But then beyond a certain value of Rex, there was a different asymptote, which was an asymptote where I said the flow ceases to be a laminar nice problem that we have. So, the purpose of today's exercise is we will try to get an overview of how do we understand flow becoming unstable, why does it become unstable, and how do we go about studying it. Now, this by itself deserves a course on its own, and there are courses which are dedicated introducing this subject and getting into at length of how we do this. So, we cannot do justice of what is actually something that has to be done in a course over a period of 1 or 2 lectures, but we will try to get a flavor of how things are done. And before you do any math in this particular problem, this whole idea is very visual. Before you get into the details of solving equations and all, understanding instability is something that is a very visual phenomena. So, you have 3 examples that you see on the top. The first one is just pouring coffee, and on that mug of coffee, inside that you pour some milk. The middle one is what is known as Laminar convection. So, the one in the middle is basically a pan of liquid that is being heated from the bottom, and you see these hexagonal patterns that are forming on the top. The one that you observe here on the left is a dripping of a liquid stream, and as you observe, after a point these are baking into these beads. Now, in the same spirit, you can actually look at other problems where here there is a liquid column, and the liquid column basically starts to develop these sinus, or varicose perturbation here. So it's bulging at some location, there is a neck formation at some location, and they start to grow. And if you observe them, after a point in time, it becomes narrow enough beyond which it can actually pinch off. So there is a jet. The jet basically is experiencing effects of surface tension, which we have learned a little bit, and then there is the flow due to the jet. And after a point, the disturbances that you are introducing, this is simulation. So the bottom ones are all simulations. This is a hot plate in the bottom, a cold plate on top. So it's kind of mimicking, each of these are trying to kind of mimic what you see in the top. So the top one here, the dripping that you are observing, that is a gravity driven jet that is coming down, which breaks up into these beads. The bottom is a simulation corresponding to the top. Here there is a hot plate and a cold plate on top. So it doesn't really have a free surface per se, but you see what you are observing here is that plumes of hot liquid are rising up because they are lighter, and the colder liquids are falling. So if you solve this problem just based on the temperature equation, you would get a conduction profile. The temperature basically linearly decreases as you go towards the top plate. Top plate is cooler, bottom plate is, so top plate is cooler, so it's basically going to keep decreasing as you go towards the top plate. A U equal to 0, no motion, is a solution of this problem for a given conduction profile. But what happens is that when you start this out, and if you are observing it beyond a certain temperature contrast, so you will have to define a non-dimensional number here, trying to understand how much of that temperature profile can you sustain, how much of a contrast can you sustain. And beyond a certain value, it's not possible anymore to have the quiescent state. The quiescent state ceases to exist, and what you see are these convection patterns that start to develop. The bottom right is a simulation done for something similar to this. So you have a combination of salt and temperature here. So temperature variation, and so density is basically depending both on temperature and salt concentration. So you can have a scenario where the top is warmer than the bottom, but then if there is also a variation of salt concentration, you can create similar instability fingers that happen. And this is something which happens quite often in the ocean, that you can have salty warm water lying over fresh or fresher cold water. So there is a salinity contrast. So if you think of temperature and salt concentration, they have different values of diffusivity. So there is a diffusivity contrast that is there in the problem, which can lead to these instability profiles. Once again, you can have a static state with no motion, but beyond a certain contrast, they tend to become unstable. And these things are quite often, it's not something that is rare. And if you even look at these individual drops, these drops after a point, they will start to basically undergo some kind of an oscillation. So pretty much along the lines of what you see in reality. So it's a very visual aspect in terms of what you observe in your day-to-day life. There are a lot of evidence of flow instabilities that are there. Obviously, it is occurring in a pool of many other things that is going on, but the fact that there are flows which are undergoing various unstable states is something that you can observe in your day-to-day life. It's not so unnatural. And this brings in a fundamental question that whatever we have been doing so far in the course, we have been primarily doing these rigorous derivations of various kinds of flows in various configurations. Would we be observing those flows? Would those flows actually been observed in reality? And that's a statement summarized here, that all the flows that occur in nature must not obey, not only obey the equations of fluid dynamics, but they should also be stable. This is the classic example of trying to balance a pencil on your fingertip. A pencil balancing on your fingertip, there is a static solution. The weight of the pencil is balanced by the normal reaction that your fingertip is giving on the pencil. So it should it's in principle a static solution, but that static solution is not stable. Any small vibration, any small motion in your finger, how so much small it may be, immediately leads for it to topple over. And that's again, something that we all are aware of, that just because that's a solution of your governing force balance doesn't necessarily mean that that is going to be observed in reality. And this is what is at the heart of how we try to understand that when flows which are very nice and regular, everything that we have studied in the course are broadly flows that are laminar flows. Laminar flows, the word comes in where the flow occurs in lamella or sheet. So you have every flow, whether a channel flow or a pipe flow, Couette flow, boundary layer flow, all of them can be thought of as stacks or sheets of flows. So very well behaved flow. There are not too many length scales or time scales in the problem. Usually in all the problems that we have done, it's typically there have been maybe only one length scale. In a channel flow problem, that's the width of the channel. In a Taylor-Couette problem, that's probably the width of the annulus that we have in the problem. If there is an unsteady problem that we have done, there's a frequency of oscillation of the plate was the unsteady effect. So there were very few length or time scales in the problem. This, if you contrast to a scenario where there are many such length and time scales in the problem, that is approaching a state which is the most disordered state in the flow. So loosely speaking, I mean, you are going to have a whole spectrum of length and time scales in the problem, and that gives us what is known as a turbulent flow. I mean, this is again a very laymanish definition of what a turbulent flow is, but at the beginning you can make a distinction that when you are looking at a flow that has a whole spectrum, possibilities of length and time scales in the problem, that is that disordered state basically takes you towards a laminar, from a laminar to a turbulent state. And the key question is the pathway. What is the pathway going from your laminar state? If you had a channel flow, what would be the pathway going from that laminar state to the turbulent state? And this is again a question which have been posed several times over the last few centuries, starting from the fact that this is summarizing what Maxwell has said, is that if you have infinite small variation of the present state, this is like that balancing pencil kind of a problem. If you give some small perturbations and the system basically stays in that rest of state of rest or in motion, then you say the system is stable. But if there is an infinitely small variation that you give to the present state and it moves on to some other state in a finite period of time, then this is called unstable state. So what happens post the instability is something that is a second question. But the first question to ask is that would you actually move away from your current flow state given that there are small disturbances that you have added? So if that is what is happening, then the system has become unstable. This is the classic way to understand whether you are talking about fluid mechanics or anything else. This is the classical approach of understanding stability. So before you think of stability, it's important to understand that stability is looking at motion, that is when you have disturbed a system, the system basically goes into a state of a completely different kind. It effectively, the system has a transition to something completely else. But before thinking of instability, where the approaches and ideas actually took place a lot in a very rigorous manner is in the theory of water waves. The theory of water waves, we will just take a very simple problem based on what we have done in class, and we will see what we can achieve from, and we'll get some of the ideas of the tools that we use typically in a stability calculation. So you have an air-water interface, and we are considering air to be a passive medium here, that is just applying a pressure boundary condition on the interface. Now what you are doing is at some time you perturb this air-water interface. So this is z equals 0 and the fluid extends all the way to z equals minus infinity. So this is an infinite pool of liquid. You can obviously make this more realistic by putting a bottom boundary and all those things, but we will just stick to this scenario where we will say that there is an infinite pool of liquid which is in contact with air. Now z equals 0 is the boundary condition that is applied, z equals 0 is the unperturbed boundary, and on the top is air. So what I am going to do is I'll perturb that interface and take it to some elevated height of z equals eta. So I have drawn it like a sine wave here. So you can choose whatever you want. For simplicity, we will just choose a sine or a cosine wave. So I will say eta is equal to some a cos kx minus omega t. So cos kx minus omega t, what that says is that it is a propagating wave. So if you are looking at this particular wave, this wave is basically propagating from left to right. So you can choose a wave that is also standing, by considering two propagating waves, but again it doesn't change anything of the analysis that we are doing. We are looking at one wave which propagates in a particular direction. Now what is k? K is the wave number or 2 pi by lambda, where lambda is the wavelength. That would be the wavelength of this particular wave that you have, right? And omega is your frequency. Now we don't know what is the relation between omega and k. So if my question is, if I give a certain wavelength to the wave, what would be the speed with which it would move? So the speed is omega by k, that is the wave speed that we have. So how fast should the wave move? Given that I have given it some kind of a perturbation like this. So now we have learned a little bit about interfacial boundary condition. So there is a kinematic boundary condition. The kinematic boundary condition was that at the fluid interface, dou eta dou t plus, I will do a 2D problem here, u dou eta dou x is equal to the vertical velocity at z equals eta, right? That is my kinematic boundary condition. We have learnt about this, that what do you apply as a boundary condition. So it remains a material surface. So if eta is the boundary interface height, then this is what we would apply. Now I am interested in very small amplitude waves, which means quantities like u, dou eta, dou x, all of these are very small. They are actually small quantities. So the initial state is when the interface is perfectly flat. Z equals 0 is the unperturbed state. So in the unperturbed state, you have water which is still, and air is basically giving you a pressure boundary condition on the water surface, a glass of water. And you know, if you give a tap on that glass of water, there will be ripples that will be created. This is exactly what we are trying to do. We are doing it in an idealized 2D problem, planar, all those things. But visually, you all can take a glass of water, give it a small tap, and immediately you will see there will be ripples. So before you have given it a tap, the surface is perfectly flat, there is no motion that is there. It's only when you have given it a tap will you start seeing these ripples on the surface. So from assuming those small amplitudes, I will have dou eta dou t is equal to w at z equals eta. I am ignoring this particular term. I am looking at small amplitudes of these waves. Now the flow that is underlying this particular wave, that is there under this interface, initially there was no motion, which means initially the vorticity was 0. So if there is no initial vorticity in this particular problem, and I am looking at an inviscid calculation, by Kelvin circulation theorem, it will continue to remain irrotational for all later point in time. So the velocity field in the fluid or in water can be represented by Laplace equation, del square phi equal to 0. So bringing our knowledge of potential flow theory. So W here can be written as dou phi dou z at z equals eta. But dou phi dou z at z equals eta can be written as dou phi dou z at z equals 0 plus eta dou square phi dou z square at z equals 0 and other higher order terms using a Taylor series expansion. Once again, I am saying that these are small amplitude waves. So I can ignore this and write this instead of z equals eta, I am going to write this approximately at z equals 0. So that's my kinematic boundary condition linearized about that unperturbed location. Dynamic boundary condition. Dynamic boundary condition basically gives us that pressure at the interface is equal to whatever is the imposed pressure from the atmosphere, right. So that reference pressure or the datum pressure, just to keep things simple, I will assume it to be 0. You can assume P atmospheric and then again absorb it in, but it is a constant pressure that is applied on the free surface. So that's my dynamic boundary condition because I am not considering right now any effects of surface tension. I have ignored surface tension in this particular problem right now. I have kept it as the bare minimum that we need to do. So we will say P is equal to 0 at z equals eta. Now what is P? How do I get P? Now the flow is irrotational. So we can use unsteady Bernoulli. So everything that you have learned, none of these things are unfamiliar to you. So unsteady Bernoulli tells us dou phi dou t plus p by rho plus half u square plus w square, it's a 2D problem, plus gz is equal to 0. It's actually equal to a constant and you can absorb that constant, it's some time dependent constant and you can absorb that constant in the definition of the potential. So I basically again put that to be 0. This entire quantity on the LHS is a constant everywhere in the flow and thus it's a constant also on the interface, and I've chosen that constant to be 0 by saying if you choose it to be something else, you can plug it into your definition of potential. It will not change the velocity field. Phi written as phi plus some function of time will give you the exact same velocity field, right? Now I'm doing a linearized calculation here, small amplitude. So which term can I drop? Which are the terms that I can drop? I can drop this, right? It's a quadratic term in the velocity. I can drop that term. So I have an expression of p in this expression. So I have dou phi dou t plus p by rho plus gz is equal to 0, right? Which means plugging it into my dynamic boundary condition, and this is all now applied at z equals eta. So this, if I plug it into my dynamic boundary condition, I will get dou phi dou t is equal to minus g eta at z equals eta. So now this again can be applied at z equals 0. So I have two boundary conditions at z equals 0. Dou eta dou t is dou phi dou t is equal to minus g eta. Now I have assumed eta to be a cos kx minus omega t. Okay. Now if you look at this boundary condition, if eta is cos kx minus omega t, then what should be the dependence of phi on kx minus omega t? Should it be cos or a sine? Eta is proportional to cos kx minus omega t, and at the boundary dou phi dou t is proportional to or equal to minus g eta. So if eta is cos kx minus omega t, then the velocity potential should have a pi by 2 phase difference, which means I am going to now assume that phi is some function of z into sine kx minus omega t. This is an ansatz I am basically making by saying that there is some unknown function of z into sine kx minus omega t. So the sine kx minus omega t comes in because it has to be a phase difference of pi by 2 from the interface evolution. Now the governing equation is del square phi is equal to 0. Del square is dou square dou x square plus dou square dou z square. Phi is equal to 0. So if you plug it in, you will get d square f dz square into sine kx minus omega t minus, sorry, the first one is x. So the first one will be minus k square f sine kx minus omega t, and the next term is d square f dz square sine kx minus omega t is equal to 0. So your equation is d square f dz square minus k square f is equal to 0. It's a second order differential equation, not too complicated to solve, exponential of kz plus b exponential of minus kz. And you have to remember what f is. F is f of z sine kx minus omega t is my velocity potential. Now my boundary condition is u and w should both go to 0 as z goes to minus infinity. The velocity field should die down once you are infinitely far away in the fluid, away from the interface. So what can you say about the f of z? Which of these terms would survive? Z is negative, which means B should be equal to 0. From the boundary condition, I cannot have exponential of minus kz, I can only have an exponential of plus kz. So your final phi is some constant exponential of kz sine kx minus omega t, and your eta is obviously a cos kx minus omega t. You have two boundary condition, the kinematic boundary condition, which is dou eta dou t is equal to dou phi dou z at z equals 0, and the second boundary condition is dou phi dou t is equal to minus g eta at z equals 0. So substitute for your, use the first boundary condition. So using boundary condition 1, I have a omega sine kx minus omega t, and dou phi dou z is a k at z equals 0. So exponential of 0 sine kx minus omega t. So what do you obtain? You get capital A is small a omega by k. Apply the second boundary condition. The second boundary condition is dou phi dou t, so that should be minus a omega exponential of 0, because applied at z equals 0, cosine kx minus omega t, and it is equal to minus g eta. So g a cosine kx minus omega t. So you obtain from here that a omega is equal to, capital A omega is small a times g. So if you substitute, you have a omega square by k is equal to ag, which gives you omega, the frequency is square root g by k. So this is known as the dispersion relation. The word is dispersion relation, which gives you the frequency of the wave in terms of the wave number for deep water surface gravity waves. The speed of the wave is omega by k, this is root gk. The speed of the wave is actually root g by k. So the frequency is square root gk and the speed of the wave is square root g by k. So with this exercise, based on whatever you have learned in class, you have learned kinematic boundary condition, you have learned dynamic boundary condition, you have learned potential flow theory, you have learned unsteady Bernoulli's equation. We are able to say that when you have an air-water interface or when you have a free surface and you use the assumptions that we have made, it's an inviscid flow, irrotational, etc., the wave at the interface, if it has a wavelength lambda, then corresponding wave number is k, which is 2 pi by lambda, the waves are going to propagate with a speed that is square root g by k. Obviously, we have made approximations here by ignoring surface tension, ignoring the depth of the liquid, but this approach, what we have done here, actually remains very useful in understanding how we look at stability of the problem. Because what you have done here, you have said that there is a frequency omega, right? So sin kx minus omega t is what you have here. So you could write this in a different form as the, or rather let's write eta, that's better. So we have written eta, I could write eta as the real part of a I kx minus omega t. I said it is a cos x minus omega t. I could write eta as the real part of a e to the power I kx minus omega t. And we found a value of omega here which is square root gk. Now, if from the calculation omega turned out to have an imaginary part, what would be the conclusion? E to the power minus I omega t, if omega had an imaginary part, then that would signify something that is growing exponentially fast. So, you would have a scenario, and we will try to do a little bit of this probably end of this lecture. We will see that if you now do the reverse configuration is that if it was a layer of water which was lying over air. Right now, we have the heavier fluid which is water that is lying below air. I never really made you think about what is heavy, what is light. But here, the heavier fluid is lying below the lighter fluid. So, the density of air has never entered into the calculation. We never made use of the fact that what is the density of the layer above. But actually, what you should have done is you should have solved del square phi also in air and del square phi also in water, and then applied the dynamic boundary condition matching pressure. If you would do all of that, then the final expression that you are getting for C would have a term that is like a density difference. So, you will have a term that would be like rho water by rho air divided by rho water by rho air, something like this. You will have a correction term of this kind. We didn't have this because we said, oh, this is just air. Air is just going to give me a free surface boundary condition. So, I have just completely ignored everything that is there in the problem of the dynamics in air. So, if you now look at this, because rho water is 1000 times heavier than air, that expression we have approximated it as 1. Now, if you do the reverse configuration where air is below and water is above, then what would happen is that this would flip sign. It is actually rho bottom minus rho top. So, it will flip sign, in which case your frequency that you would get would turn out to be imaginary. An imaginary frequency is going to something that will lead to a growth, because you all know that it is impossible to see a configuration where there is a nice static state of water lying over air. You all can see a glass of water where air is on top, water is below. Invert that water and you will have water spilled all over you. Now, is it because you have done it carelessly? So, you can now put a lid on top of the glass, turn it around, and as slowly as possible, with the most precise manner, you try to pull the plate away. You will still have water falling through. It's just like the inverted pendulum. You cannot have a heavy liquid sitting idle over a light liquid, especially for something like water and air. Obviously, like you can make the density contrast becoming very small and then surface tension can come to your rescue, but from the point we are talking about, this is the essence of what we are thinking of. A layer of water over a layer of air will satisfy your hydrostatic equations. You can solve for the hydrostatic problem, right? Dou P dou Z is equal to minus rho G. So, you can find the pressure variation going from a heavier liquid to a lighter liquid. Nothing stops you from finding that static solution. There is no flow, there is a pressure profile that you have, which basically is associated with the heavier liquid on top and lighter liquid in the bottom. But the purpose of doing all of this is that in that configuration, instead of seeing nice ripples, you are actually going to get an instability. So, this detour was to actually talk about water waves, and this is the example that I was telling you about, that when you have a glass of water, if you do this as a simulation, when you have that axisymmetric kind of a geometry, so when you give it a tap, you are going to see these kind of ripples. Whatever you are seeing here is basically the cylindrical or the axisymmetric analog of what we just derived in the last few minutes. So this is how most of it actually started out, and obviously there's a lot more that goes on after that, but the primary point, starting point is coming from water waves. Trying to understand that when you have an interface between two liquids, it's a static solution is there, but that static solution is something which you will not observe when you add disturbances to the system. So we saw waves, but in some cases it can become unstable. So the pioneers of hydrodynamic stability, which again started from the problem of trying to understand that is flow through a pipe or flow through a channel going to be observed irrespective of whatever pressure drop do you have. And that is something which primarily started with Helmholtz, went on to Kelvin and Rayleigh, and what is a legendary set of experiments done by Reynolds of Reynolds number fame. The experiment that was done in 1883, you can see the setup for yourself here. So you have a pipe which is submerged in another liquid and it's controlled by the head. So you basically keep playing with the amount of pressure drop that is actually there. And what you observe that with the increasing flow, so there is a dye that is injected. This is experiments from Reynolds' drawing of what he was observing, that when a dye is injected into the tube, the dye remains nice and orderly or nice and a single line when the flow rates are low, but with increasing flow rate, it starts to take this kind of highly disorderly states. And in this particular paper itself, I mean, he also came up with this whole point that there is this non-dimensional quantity which distinguishes these different experiments. He didn't call it Reynolds number, but he gave this measure of something what we have as rho UL by mu that every time appears in our Navier-Stokes equation. So he came up with this fact that instead of separately trying to see the velocity or the length or the viscosity, it's this one single non-dimensional quantity which is controlling this kind of a transition. So you are playing with this inlet parameter, and if you keep everything else fixed, you see that the flow, the dye basically being a proxy or a signature to understand that the flow is not as nice and laminar that you have. The parabolic velocity profile that we are talking about, that parabolic velocity profile ceases to be there. So there are many who have attempted to do this at various stages. So you have various historical figures who we have come across during the course, Rayleigh, Kelvin, and some of these calculations were also erroneous. Historically, to understand this particular problem and understand what is going on theoretically was also the PhD thesis of someone who you have heard in a different context, Werner Heisenberg, who you know more probably from quantum mechanics. So his PhD thesis was actually trying to understand this transition problem. So it's pretty historical in terms of what has been done for that particular problem. But a problem where this was done remarkably well in terms of looking at experiments and theory, where you do the theoretical calculation and match it with experiment, it was done by G.I. Taylor. G.I. Taylor did a lot of different, looked at different scenarios where instabilities are very dominant. So there are three here. First one is where you are trying to spread or inject light or low viscous fluid into a more viscous fluid. So imagine that you have a scenario where you have a very viscous fluid that is there, and now you are trying to inject into it a lighter fluid. So as the lighter fluid is going to spread, so you are looking at it from the top, and this is actually something that is of quite a much of an importance in a lot of oil extraction porous media problem, where you have a very viscous fluid that is already there and you are trying to inject a light fluid, and as you can see here, it doesn't spread out in a nice axisymmetric manner. It starts forming these kinds of fingers. So you will have these fingers which will start to form as you are displacing a more viscous fluid by a lesser viscous fluid. So that interface becomes unstable, and this is known as a Safman-Taylor instability. This one is exactly what we were discussing a few minutes back. A heavier fluid which is sitting on top of a lighter fluid. So the blue is a heavier fluid, you can think of it like water, yellow is lighter fluid. So now with that, if you think of the static problem should look exactly like this. The color coding is to give you the concentration or it's like a marker for that particular fluid. Now the interface you can think of this as a miscible fluid, you can also think of it as an immiscible fluid. So, if there is an immiscible fluid, then there is a surface tension which is going to act in the problem. So, you will always see like boundaries between blue and yellow. If it is miscible, then they are going to nicely get mixed up. So, when you start the simulation, if you look at the interface is basically starting to grow, and gradually you have upward moving bubbles of the lighter fluid and downward moving spikes of the heavier fluid. So, you see these mushrooms that are actually, so it is an accelerating interface, because at the interface there is a density jump. So, you have these mushrooms which are moving up of the bubbles, and then the spikes are coming down, and gradually if you wait long enough, you will start to see this kind of a pattern developing. So, again this is a static solution. Even in this particular problem, the left one, the displacement of the more viscous by the less viscous fluid, there is a solution that you will have from the governing viscous equations, where a nice circular interface will be a solution. You will have a displacement where you match the tangential stress, you match the normal stress, and you will find that the circular interface between the radially propagating less viscous fluid over into the more viscous fluid is a solution of the problem. Just the same way in this scenario, but these are not stable solutions. The last one, which is what we will actually look at, comparisons from Taylor, this is also something we have done in class. You have concentric cylinders. When we did laminar viscous flows, we did problems in pipe, channel. We also looked at the problem where the two cylinders are concentric and they are rotating differentially, which means that both are not rotating with the same angular velocity. Now, if you have a counter rotating scenario means that your inner and outer are not rotating in the same sense. Or you can think of a scenario where the outer is held stationary and the inner is basically spinning. So, you can show that this kind of a configuration is centrifugally unstable. Centrifugally unstable means that if you look at two rings of fluid, you find out what is the angular velocity here, omega 1 and this is omega 2. This is radius A1 and this is radius A2, just two rings of fluid. Now, if you were to swap these two fluids, each of those fluids, you basically do a switch of these two fluids, then what would happen is, instead of the outer fluid moving inwards and the inner fluid moving outward, means coming back to their rest state, they are actually going to move away. So, the angular momentum is such that they are basically going to go towards a more unstable state. So, this was the experiment that which Taylor tried out. I mean, and these things have been done repeatedly in the lab over recent times. So, if you see initially, when we derived in class the angular velocity for this, if you remember, the angular velocity had this is not the angular velocity, this was the azimuthal velocity. The azimuthal velocity we derived in class had this particular form. The constants A and B were obtained from the boundary conditions. We applied the boundary condition that u theta is equal to omega 1 r1 square on the inner boundary, omega 2 r2 square, omega 1 r1 on the inner boundary and omega 2 r2 on the outer boundary. And then applying those boundary condition, we got A and B. There was no ur, there was no uz, u theta was only a function of radial coordinate. Once you keep increasing the speed of, let's say, the inner cylinder, what you start observing is that there is a pattern that is developing in the z direction. The solution in class which we got, there is no z dependence. You don't have any z dependence in the solution we got in class, right? It was purely a radial solution of a swirling flow. But when you do this in experiment with increasing rotation speed of, let's say, the inner cylinder, beyond a certain critical value, you see this very nice periodic wave pattern that is developing. So, what you are actually getting here, you are getting donut shaped vortices that are forming, toroidal vortices, a stack of toroidal vortices. Think of like a tube and you put a lot of cycle tires one after the other. So, you have created a stack of these cycle tires. So, that is what you are getting, and if you continuously keep increasing this, again none of this is all Okay. So, if you keep increasing this, you see finally it gets extremely disorderly. The whole pattern, it stops even losing its axisymmetric nature. So, in the initial stages, it is something that is axisymmetric. It breaks the axial symmetry in terms of the fact that in the z direction it develops these periodic behavior, but in the azimuthal direction it is still symmetric. And gradually with increasing flow rate, you start seeing these becoming more wavy. There is some kind of a waviness that is developing also here, and finally it goes to a fully turbulent state where it develops significantly more number of length scales and time scales. So, this is what is from Taylor's original paper, and this is why it's quite important to appreciate this particular paper, because there are few things which are there in this paper. Taylor did this experiment. Taylor also did the calculation of the instability. So, he actually found out, and you can make note of when this was all done. He actually computed what is the boundary of instability. There are two parameters here, the cylinder rotation rate of the inner cylinder and the outer cylinder, and you also have the values given in his experiment of R1 and R2, the inner cylinder radius and the outer cylinder radius. You can see the gap is very small, it's not a very large gap. And what he observed is that the prediction that he got from his numerics in 1923, over 100 years back, and that from his experiments, you can see how remarkably they are on top of each other. So, this is a fabulous set of calculation that was done, which kind of established how well prediction from this, that you have seen in class, there is a velocity profile which is a combination of a solid body rotation and an irrotational vortex. This is what we got in class. We found what those constants are. That solution is not stable beyond a certain value of inner cylinder rotation rate. If you keep spinning the inner cylinder faster and faster and faster and faster, so let's say if you make the outer one stationary, which is this location, as you keep spinning the inner one faster and faster, at some point the flow ceases to be stable. You don't see that stable flow anymore. You start seeing those stacks of toroidal vortices, and this is exactly where you phenomenally have this kind of a prediction, where what you have observed in the experiment lies exactly from the predictions of a linear stability calculation. So, the linear stability theory got its main push when with this quantitative agreement that was obtained. So, you got a very precise quantitative agreement between your experiments and your theory, which made linear stability theory as powerful as it was before. So, there are several achievements that are there. There is Taylor-Couette, which we spoke about, and then there is Rayleigh-Bénard, which is where you have the hot plate in the bottom and cold plate on top. Rayleigh-Bénard is where it is basically unstable due to density stratification, whereas Taylor-Couette is basically where you have stratification that is unstable due to angular momentum. So, in Rayleigh-Bénard, if you take a parcel, so the temperature is cold on top and it's hot in the bottom. So, if you take a parcel from here which I have shaded and you swap it with the parcel which is on a higher elevation, what would happen? If the hot parcel goes to the location of the upper level, it is now surrounded by lighter fluid. Sorry, it is surrounded by heavier fluid here, right? So, I have a lighter fluid here and I have heavier fluid on top. So, if I switch the light and heavy fluid, the lighter fluid, when it is surrounded by a cooler or a heavier fluid, it is going to keep going further up. Similarly, when I bring the heavier fluid here, it is now surrounded by even lighter fluid and it sinks further down, which means that they never come back to their original configuration, they separate out further, and that is the way to understand the system has become unstable. In the same way, you can argue also for Taylor-Couette. Now, that is where things are great, but things get a little dicey when you are looking at other problems we have done in class, a plane channel flow, a pipe flow and a Couette flow. So, this is where the question remains is, whatever we have done so far, would that still continue to give us a prediction based on how we have done it? Okay.